All right, so welcome to geology, everybody. Time for igneous rocks. So what are they? And this note sheet will be up there if you want it. And then the other one that I posted, you can fill some stuff in there. Should you want to kind of summarize it all in one place, you do you. How do you want to do it? So these are rocks that form from the solidification. Change color here. A little bigger too. Which requires cooling of magma or lava. All right, so we'll take melted rock and cool it. And really don't overcomplicate that. It's going to get more complicated, but don't, like, in a sense, you've done this with water. You've taken water that's warm enough to be above the freezing point, liquid water, and you've put it into a freezer and you've gotten it below the freezing point and it's turned into solid water. Think of that as a starting point, and then we'll overcomplicate our lives in a few minutes. So let's just jump right into like how to identify them, and then we'll talk about where they come from and all kinds of fun stuff. Your two jobs really are going to be to observe a rock's, and this sounds hard, cooling history and composition. If you pick up one of these rocks and tell me how quickly it cooled, that sounds hard, but you'll find out it's not too bad. And composition, what is it made out of? So we'll start with cooling history. We'll go with two very basic scenarios. Down here, we'll say we've got hot magma within the earth, which for various reasons, and we'll try to get into this in the bottom, at one point goes from being that kind of sticky Play-Doh like, flowing solid into a liquid. And again, keeping life simple, we'll go with two options. It either works its way all the way to the surface and comes popping out. Those are great arrows right there. In which case, we say, hey, that's a volcano, right? We call it lava when it comes popping out of the surface. Those are going to be your extrusive ones. And some works its way towards the surface, but doesn't quite make it all the way and is within the earth, in which these are going to be the ones we call intrusive. So exploding onto the earth, intrusive, forming inside the earth. So how can you pick up a rock and tell this? The way it works is that if they're extrusive, if you come out onto the surface of the earth, even on a very hot day, and you're lava, it's cold up here, right? So when you get up here, the lava is going to cool quickly. That's its cooling history. And again, how do we tell? We'll find out. Whereas if it comes up inside the earth but doesn't quite make it, it's insulated by the overriding layers. It's still close to the inside of the earth where it's a little bit warm. This is going to cool slowly, like a big thermos, So what does that do? Well, these guys that cool very slowly, what we got to get into is where the analogy of water versus lava, this is where it's going to get more complicated. Water's made of water. So you take a water bottle and you freeze it, you got solid water, H2O. You take lava, it's made of a whole mixture of minerals. So what happens when that cools is that these minerals individually can start to like crystallize and get bigger and bigger and bigger and bigger. And the more slowly they cool, the more time they have to get bigger and bigger and bigger. And what that's going to result in is that these are very coarse grained rocks. Now, let's throw a definition out there for coarse. I don't mean how it feels like on your skin. If you were to pick up one of these rocks and like feel it, that's not coarse versus fine. What I'm talking about is how big are the grains within the rock. I do recommend playing around with your textbook here a little bit. Sorry, I should have set it up already. So here's what I'm talking. Larger bits that you can visibly see. Larger bits you can visibly see. You can visibly see those even though they're all dark in color. Versus what we see down here. If we get rock that pops out onto the surface of the earth and it cools quickly, those individual minerals don't have the time to form very big crystals. So what you end up with are fine-grained rocks. Now, a couple other kind of funky things can happen here. Actually, let's check out the fine grain first in that diagram. You can't really see the bits that make up this rock, right? Those you can see. These you can't really see them very easily. They're microscope, sure, but you can't see them with your naked eye. That's what I'm talking about with fine grained, coarse grained versus fine grained. And again, it's not what it feels like. I can tell this piece of granite is like polished, like a countertop. It doesn't matter what it feels like. That's a coarse grained rock because you can see the bits that form it. So that's your fine grain. Now, a couple other, like I said, funky things can happen. You can get also up here something called vesicular, which means it has gas pockets, like Swiss cheese almost. Little fine gas pockets in there that form, and we'll get into why that happens. Or you can get glassy textures, volcanic glass, obsidian. A lot of people have heard of that. So all three of those are really a result of on the cooling on the quicker side. All right. So again, if I were to have handed you these rocks and said good luck, there's our first step. I could separate out the ones that look like they're coarser grains, therefore had to cool slowly, from the ones that are finer grains. Halfway there through this page. Composition, how do I tell that? Well, there's different minerals in the lava, in the magma, and we've got names for those different compositions. There's felsic and there's mafic as endpoints, and then towards the middle is intermediate. And these are not strict categories. It's like a continuum from the more felsic side over here to the more mafic side. So what do these mean? Felsic has more silica and aluminum in it. Great. How do I pick up a rock and tell that? They will tend to be lower density. Okay, that kind of helps if I pick it up and it feels like a little lighter versus one that's a little heftier. That's great. And then the big giveaway is that they're lighter in color. And specifically, if you see pinks in here, that's a big giveaway. Up over here to mafic, we've got more iron and magnesium, higher density, and darker in color. So there you go. Like, this feels complicated, but at the end of the day, it's the most like discrete ones that you'll have. You'll be able to tell just by looking at those. Okay, coarse versus fine, light versus dark, and like job's done. When we do sedimentary and metamorphic, it's a little more challenging than that. These like might be the hardest rocks to kind of visualize, but that makes it really, really easy to figure out like that. All right. So I won't fill this out. I'll have you guys take a stab at this. What would it look like if it's extrusive and felsic? Maybe I'll do one to kind of give you the idea. So if it's extrusive, it would have fine grain. Felsic, it'd be lower density, light in color. See if you can figure out the rest of those, which shouldn't be too bad. Except I suppose I didn't talk about intermediate, which is just kind of everything's in the middle, right? Looking at this guy. So we got our light color with the pinks. We got our dark color. This is going to be the in-between. And if you say, hey, maybe I think that's light in color. First off, most diorites I see are more 50-50 black and white. But that's why I write pinks over here. When you see pinks, we know that we're over on that felsic side. When you see the more grays to somewhere in the middle, you know you're in the intermediate, and then darks will look like that. All right. Excellent. So give that a go. So let's just like throw this down to get it on paper. Texture refers to the like nature of the minerals in the rock. Again, not how it feels. Are they large? Are they small? Is it vesicular? Is it like gas pockets? Is it glassy? So what is that? An igneous rock that contains gas pockets is what we say vesicular is. And the why is because the release of gases, really, I mean, CO2 being a big one. Oh, that goes over here, my bad. Because of the release of pressure, it allows, let's go CO2 there. Sorry about that. This sudden release of pressure, which allows CO2 to convert to a gas. So picture a volcano with some pressure on it. It's capped, right? Simultaneously, put this example in your head, even if it feels weird for a minute. Take a 2-liter bottle of soda that's got pressure in it, right? That CO2 is in the liquid. So if you shake it up a little bit, you get a little angry, right? When you release that pressure, because that pressure is no longer forcing that CO2 into the liquid, it comes out and there's bubbles, right? So if you could like take soda bubbles that come out of the top of that thing and like instantly solidify them, freeze them, you would have a vesicular piece of soda, solid soda, I guess, right? Do that same thing in your head with a lava. It comes popping out. That CO2 converts to a gas, turns into bubbles, but then solidifies. Because it's extrusive and it cools very quickly, it solidifies and it preserves those bubbles of gas in the rock. Glassy. Sometimes a rock cools so quickly that really truly within the definition and the nature of a mineral, it's kind of like minerals don't form. We haven't done what the definition of a mineral is yet, but this is kind of an amorphous glass. It doesn't have necessarily the mineral structure that it might. If you've ever seen obsidian, that's the case. Let's look at the book. I'm going to pause quick. So there you go. There's the images from the book of vesicular, the little tiny gas pockets. Obsidian, generally the poster child for what those glassy ones look like. And this little chart right here, table 7.1, pretty good breakdown of what we just talked about over here. All right, so get yourself some sort of way to crack this all out and get it on paper. There's different igneous rock IDs out there. Use this one in the notes, look up some on the internet, use the one from your book, which is that one I was using with the felsic, the intermediate, the mafics, and the ultramafics. Let's put those on hold for a hot minute here. So this one breaks it down by the felsic with those felsic minerals in it, the intermediate with those intermediate minerals, and the mafics with those mafic minerals in it, form those rocks that then are either coarse if they cool slow and fine if they cool quickly. I wouldn't advise trying to memorize all this. If you're a geology major, it's going to happen soon enough. Start to work it, but trying to jam that whole thing in your head, getting ready for a test on top of everything else, I think would be a lot. So get it down somewhere where you can use it. Now, like this looks like a mess. This looks intimidating, maybe, right? But let's break down how it looks. It really tells us everything. For our felsic rocks, which have a lot of silica and aluminum in them, they are lower in density and lighter in color and contain these minerals, and will be rocks like these ones. For our mafic rocks, which have iron and magnesium, they're higher in density and darker color, use these minerals and will make these rocks. How do we know which rocks? The intrusive rocks, which we got to know, I suppose the one thing you'd have to know here is that these cool more slowly. The extrusive rocks, which we'd have to know cool more quickly, would have these matching textures. They'd either be coarse, or if they really cool slow, very coarse, you can get a pegmatite. Whereas the extrusive ones, either fine, vesicular, or glassy, will form these rocks. So it's really like almost like a scary looking version of playing Battleship. What column is it? What row is it? Line them up, and there's your rock. All right. Why don't you try a few questions? How should I do this? Maybe I'll post answers, or maybe I'll post a quick video to go over some of the questions that are in here. I don't want to do it just on the camera though, because then I don't know, you won't see it. All right, continuing our trip down complicated lane, Bones reaction series. Let me just pop it up over here in the book, which goes back to this idea that, okay, water is an easy way to picture this. You go from a liquid, you cool it enough, you get a solid. Magma, okay, same deal. You get a liquid, you cool it down enough, you go to a solid. But those are made of multiple minerals. And as it turns out, those minerals have within them different cooling temperatures, different like solidification temperatures, maybe a better way to say it. Freezing points, essentially. So what's going to happen is as it cools, different minerals will crystallize out at different times, which can go and in fact change the very nature of the magma. If you say you've got a magma with this composition and you start to cool it, but you're pulling some of those minerals out because they solidify, what's left over? Well, everything but that mineral. And then you cool it more and you lose those, and you cool it more and you lose those, and you cool it more and you lose those. And you can end up changing the nature of it as you go. Now there's some diagrams in here that show that, and there's some stuff that's complicated in here. I'm going to try to make the questions kind of as base level as I can, where if you check some of this out, they won't be too hard. But what happens as it cools and certain minerals form? Check out this section of the book. Take it slowly. It might take a read or two to get through some of that. Here's another example, or just again, go to Google Images and throw Bowen's reaction series. You'll see tons of them, tons of different ways. I mean, they're all basically the same, but different representations of it. Since magmas are a mixture of minerals, and different minerals have different, let's call it freezing points. Therefore, some will crystallize out first at higher temps, and others need to cool off a bit before they form. So here's another practice question. Again, I'll leave that there. See if you can think about how that works within Bowen's reaction series. All right, so then in the last unit, tectonics, we skipped over volcanoes. Let's jump back in and think about some volcanoes here. Because what happens, you've got different types of volcanoes that will form based on what composition of lava is coming out them. And that's what that box is, composition. Sorry. And really what it boils down to, more than anything else, is the amount of SI in the lava. That has a big effect on the viscosity. So let's go back and look at this. Over here on the felsic side, rich in silica. Over here on the mafic side, we have less and less and less. And that has a big effect on, if you take that mixture on the felsic side and that mixture on the mafic side, and you had magical hands that could hold them both, hold hot lava, you would denote a big difference between the two. Because what it does is it changes the viscosity, which is resistance to flow. In simple terms, how sticky is it? More like peanut butter or more like water? And there's the hands example. If I held peanut butter in one hand and water in the other hand, you'd get a sense for how those are different, right? If you have a very sticky lava and a very runny lava, you would know that difference, right? So let me pull up that chapter and look at a couple of those diagrams. So to look at them kind of as endpoints, this diagram does a great job right here from your book, figure 11.22. So the very sticky composite, the very runny shield. Now, here's the thing. I've never been out to the Northwest to see any of these things, but if you were to go to Mount St. Helens, Mount Hood, one of those guys, and you were to say, wow, that is a giant mountain, here's a drawing of what that might look like. And it's big. I'm not saying it's not big, it's not great. But when you were then to go and look at a shield volcano, they're outrageously large. Because a shield volcano like Hawaii, keep in mind that not only is that a great big island with people living all over the place, it also has to go all the way down to the bottom of the ocean. And when you pile up that much rock, it sinks in. Remember that whole isostatic balance thing we mentioned? It sinks into that squishy layer of the earth. So as it gets bigger, it also settles, meaning that these things are just monsters compared to the composite ones. Now, I mean, this is drawing, right? Not perfect, but just to get that idea that the shield ones are huge and the composite ones then are relatively small. But explosiveness is going to be the thing. And this is going to be like, look up some videos of Mount St. Helens going off in 1980. And, bad news if you're nearby. It was bad news for the geologist that was there studying it. Versus these, you can go and be reasonably close to these and watch these non-explosive. If you've seen like the videos of like them if it flying out the vents, yes, but that's not what I'm talking about with explosion. That's like the pressure shoving it out, right? But when it hits and when it's just flowing, you can watch it flow down the sides of the mountain and be reasonably close and even outpace it sometimes depending on how hot it is. And that all comes down to how sticky that magma is. So use your brains. What would the composition of those be then? And then think about like what, so maybe I'll add that in here. So what rock might you expect? That'd be great. So if you can figure that out, let's put that down here. What rock would you expect that to be made out of? Like Mount St. Helens, what rock would you expect that to be made out of? Like the Hawaiian volcanoes. If you can figure that out, you're doing pretty well. All right. Last thing, I wanted to do two more things, but one was In that other document, I said, let's do where in New York do you find these rocks? Igneous is the one where there's by far the least in New York. There's not a ton of it. But one very prominent, one that you can see, especially for our downstate students here, is the Palisade Sill along the Hudson. Let me just pop up a random image of it. I should have done that already. So visible right along the Hudson River. I mean, you can see it from parts of Manhattan. Great big cliff with the Hudson going by. There's a good one right there. All right, so what's going on there? What is a sill? This section of the book down here has great diagrams of all the different ways that you can get. Here we go. All the different names that go with the different ways that these igneous intrusions might take place. Dikes, sills, laccoliths, things like that. So check that out a little bit. So what a sill would be is one that works its way out that way. So why does that form such a big cliff in New York? Well, that's what we got here. This would be a diagram. I don't know if I can make that bigger without messing it up. Of a cross section. So looking from parts of New Jersey over towards where the Hudson River lives. A fault that right there has filled in since. And then with some extension has allowed this intrusion of igneous rock. So the Palisade Sill extends out like that. So that's what I'm saying. It extends out sideways from the original intrusion over there. And given that it doesn't weather quite as easily as other rocks, it's left us with this big cliff right there. So that, I mean, you are a tiny, tiny, tiny little organism in this diagram, barely visible, right? So the Hudson River would be flowing right out here. I mean, all of New York City would barely be visible on this diagram. All right, so the last thing that leads to that I'd like to talk about is why does rock melt? It really comes down to three things. Let's jump in with this one. Compression. So this was during a time where there was rifting going on. That should hopefully ring a bell from back in the tectonics unit. That means the crust is going to be getting thicker. I'm sorry, thinner and thinner and thinner. There's less pressure on the rock, and when that happens, that amount of pressure on there is one of the factors that determines that freezing point. If you take less pressure, it's more conducive to allowing that rock to turn into a liquid, and it allows it to come squirting up through the crust like that. Number two is like an obvious one, addition of heat. Like around mantle plumes and hot spots, things like that. If you get it hotter, it's clearly going to be more likely to be a liquid. And then we'll go to subduction zones. Like think water. Really, addition of water is what I should just stick with here. If you add water and you have a pretty good diagram here. Let me find this. Let me last pause. Sorry, everybody. So you'd have to see it graphically here that if you add things like water into it, the like where the melting curve lives changes. So that can be in subduction zones where that crust that has been at the bottom of the ocean carries that stuff down into the planet and aids in melting. Because again, we should think when we looked at all those layers of the Earth, talk about how, hey, it's not all liquid. Remember, the only one that really behaves as a liquid is the outer core. So if I sit here and say, well, there's liquid magma coming popping out of a volcano, you might say, well, hey, what the heck? You told me that this part wasn't liquid, it was solid. So what can we do to change those amorphous solids into liquids? Those are the three. Take pressure off of it, add heat, or add water are really the big three that can do that. All right, check out the rest of chapters 7 and 11. Shoot me an email if you have any questions. Hope you're doing well, everybody. Thanks for sticking with me. Take care.